Okay. Okay, guys, let's get started for the day. Today, for the first time, we have the students from Waterford Institute of Technology 2, and Dr. Walsh is with them. And here we are in the CMU IoT class as well. And just to introduce myself for the folks in Waterford, I'm Kumar Yalamarthi here. I'm a faculty in the School of Engineering. And along with me, right across me, are the senior electrical and computer engineering students, the fourth-year students here. So, and you will see them momentarily on the screen. One of my TA is signing on the WebEx, and he is going to broadcast the students as well.
Oh, okay.
So, let me see if I can get this little recorder button on the side, and there we go. We're almost there. Oh,
yep, that's
looks
it.
like I can't get this recording one into the background, I guess, but that's okay. We'll make do with what we have. Just like in the last lecture, I'm trying to record this lecture, and we'll post it on YouTube down the line for the students in Waterford or the CMU to look at it at a later time. And Dr. Walsh, I presume you talked to them about the project so far?
Yes, I went through the same slide deck we went through last week, Kumar, in the last 45 minutes, so they're up to speed.
And you said probably there might be a few more students signed up for this class?
Yes, luckily we're joined here by the automotive stream from Applied Computing, which kind of lends itself well to the topic that we've picked for project.
And how many do we have there right now, approximately?
In the class at the moment, we have 6. We have 8, but there are a few students missing.
Okay.
So I think in total we're going to have around 12, 13 students.
12, 13 students, great. So we have about 17 students, so some projects could be like an even split, some projects could be like a 2-1 or 2-2. It'll be great.
Yeah.
And the students are already thinking about projects. Some of them have good ideas here, and we'll get them going pretty soon.
Yes.
Okay, so that I cannot change anything right now, so it should be use the same link as before. It's not. Okay, looks like broadcasting the students' classroom is not feasible at this point, so we'll broadcast the students' picture in the next class. But probably you have to see my face and live with it, I guess. You're stuck with me for the next hour.
All right.
So, anyways, today we're going to talk about sensors, which is one of the most important topics in IoT, in my understanding. I mean, I would presume Dr. Walsh would agree with me on this. So we're going to start off with, what is a sensor? Before a sensor, we're going to start off with the transducers. What are transducers, guys? I'd like to hear from you guys. I mean, you're here. So what is transducer? Something that takes something, converts into something else. What is that? Fill in the blanks for me. Converts a signal from what to what? It's a device that converts some kind of energy that we have into a corresponding electrical signal here. The whole point is, if you're trying to acquire temperature in this room, we got to use some kind of a thermistor or some kind of a resistor or thermocouple or something that takes the energy in the air, that transforms it to some kind of an electrical signal, so we can process it, we can analyze it, and take an action from there. Okay. So when we say transducers, there are two types here. The first one is a sensor. The first one here is a sensor. Okay. A sensor takes a signal from the real world, which is something like temperature or humidity, and converts it to an electrical signal and gives it to something like a microprocessor. Right? That is the first one. The second one is an actuator, something like maybe a heater or maybe something like a motor that can take electrical signals from the microcontroller, okay, and process it. And if you want to activate a motor, to turn it on, or if you want to turn on a heater to warm up your room, you can do that. So transducers are basically two things: sensors or actuators. So for an IoT system, which one do we need? One or the both? Most of the times we need both, right? You got to acquire data, you got to analyze it and take an action. If you're just acquiring data and analyzing it without taking any action, is there a point in designing a system as such? The whole point of collecting data is to take some kind of an action. So you need both a sensor and an actuator here. So now we're talking about sensors. The sensors, there are two types of sensors, which is a primary transducer, the secondary transducer here. Okay. And the primary transducer here, it takes the real world data and converts that into some kind of electrical signals here, right? When we're talking about electrical signals, it converts it to some kind of an analog signal here, okay? Analog voltage or current signal. And the secondary transducer will take any particular values here in the analog signal and converts it to something like 0, 1, 1, 0, 1, 1, 0, 0, right? It converts it to some kind of a digital form. Do we need to convert it to a digital form? Yes? No? Why? I mean, we are giving all the signals here to, as we said, we're going to give it to a microcontroller, right? Microcontroller, what is it, analog or digital? It's on a digital. So do we have an analog microcontroller? Is this possible to design one? You can have analog and digital inputs, you're right. But can we design a microcontroller that operates purely on analog-based signals? No. Actually, the world's first computer was an analog computer. We moved from analog to digital domain. So you can still design a computer to acquire analog signals and process analog signals, work in the analog domain, but it is not going to be portable. It is not going to be power efficient. Okay, these are the two major things now, right? We want something to be operating rapidly fast, and we want the device to fit in the palm of our hands or deploy and remote applications and operate on a coin cell battery. In order to do all this, we need digital signals. And the digital signals are obtained using the secondary transducers. And we will talk about what these are probably in the next class, which are primarily analog to digital converters. We will talk about it in the next class. So, what kind of data can we obtain and what kind of sensors do we have? So we can obtain data such as my voice. My voice here is an acoustic signal. We can acquire that, which is what this microphone is doing right now. This microphone right here is acquiring my voice, and converting that to an electronic signal here inside. That is converted to a digital format through the USB and goes to the computer. Right? So we have one signal right here. How about biological or chemical? Anyway, are they important? Yes? No? Yes? How about optical? Light. Is light important? Especially if you're driving in the middle of the night and if you don't turn on your lights. I mean, most of the time when I'm driving, I forget to turn on my lights. And you have the cars right now that can sense your light outside and turn on the lights automatically for you, right? I don't know if you guys have been in this situation, but when you drive across the state, in some places, the regulations to turn on the lights of your car in moderate darkness is very high. Like Michigan is very lenient, but go to Ohio, if the light levels are very moderately low, you're required to turn on the light. And if you do not turn on the light, you get a ticket. Okay, so the Ford Motor Companies and other automobiles, they try to automate the systems, so one less thing for us to do, right? So electrical signals, there is light signals. How about mechanical signals? How about mechanical signals, guys? Can we acquire mechanical signals? Like speed, the speed of your car, or velocity, or how fast you're braking. Is that important? Let's say if you're driving and if you hit someone and that information is not acquired, will your airbags deploy? If the information is not acquired. Yes? No. So there are different signals, right? Sensors are very important, is what you're saying. Oh boy, looks like we have a problem there. Dr. Walsh, you hear?
No.
We can hear you. Okay. I'm going to pause the recording for a second. Okay. Let's talk about robotics. Do robots need sensors? Yes. Why? Yeah, I mean, they don't have a brain. They cannot see. They cannot touch. They cannot feel, right? So, yes. They need a control system. They have to think. In order for it to think, they need information about the vicinity. And that information is obtained using something called sensors. Like, have a robot in the hallway and have it move around the building. Or like your Roomba, the vacuum cleaner in your home. Unless it knows where it is, unless it knows what's in front of you, it cannot go and clean the house, right? So knowing where it is, that is called localization. Okay, we need that. Okay, now how about cars? If you have cars, if you're driving autonomous cars, think about an autonomous car. You sit in the car, and can it driving autonomously without no sensors, and next thing you know, your car and you both together are in a junkyard, right? So we have to know what's in front of us all the time. And are we going to hit something? We got to know if there is any obstacle in the path. Okay? Now, how about in agriculture? I mean, agriculture is done predominantly by humans right now, but we are going to the mode of automation. How can sensors be used in automation? Yeah. Uh, yeah, right now it is just beginning to start, but there are farms right now that where you have, like, say, for example, if you have oranges on a tree, oranges do not grow in a particular area of the tree, right? They grow all around. And if you take two trees, the layout of the oranges, the placement of the oranges is not uniform. And the shapes and the sizes of oranges are different too, right? And the ripening time is also different. So how can we use sensors to automate it and increase the yield? So one of the projects done by some folks in Pennsylvania is they have an orange farm. They're deploying drones with a camera, and the drone flies around the orange farm and geotags each and every orange on each and every tree. And that data is fed into an automatic plucking system on the robot. That data is downloaded into the map, and the robot will go around and pick only the oranges that are ripe. Okay. And the point is, increase the yield rate, because do we waste a lot of food? Yes, a lot, right? And that is where things are going into right now. Automation to increase the yield rate, minimize the wastage. Autonomous harvesting is where we're going. Or warehouses. Do we need sensors for these robots? This is like kind of one of the robots used in the Amazon warehouses. Do we need sensors for these? I mean, if you ever look at a video of the Amazon warehouse, there are, like, this orange one right underneath the crate. There are thousands of these robots going around one autonomous warehouse. Thousands of them. Okay. And they have to know precisely where they are. Or, like, if you take something like this one, okay, an autonomous robot, put a forklift on it, and the forklift comes in, and we have this pallet, right, on the bottom here, and it has to know this precise location of the holes. And if it doesn't, if it pushes it onto the side, you might even tilt the whole rack and you can throw it off. And then it's a huge safety concern. Yes? So you need sensors for that. What kind of sensors do we use for that? For this kind of finding the holes in the pallets, what kind of sensors can we use? Proximity sensors, yes. What else? Like, we have to see the holes, right? We have the forklift or the robot should literally know its location. Proximity tells you how far you are if you are close, but you'd have to identify the precise location. So you need some kind of a vision, some kind of acoustic signals as well. Okay, we'll talk more on that slowly. Okay, how about for something like this? I mean, on the right side, this is a project done by Microsoft. One of the recent projects was here. On the left side, we can just identify the faces, right? I mean, here, we are identifying the faces and we can recognize if there is a human or not. But look on the right side image. There is a number and there is an image corresponding to each face. What does it say here? Male or female? And age. Think about it. Yeah, in a way it is creepy, but I agree. But there is a lot of information that you can obtain. Right? I mean, if you're in a business sector, if you're trying to acquire information, there is a lot of intelligence that you can input. And this was, by the way, guys, it is not new. This was done 2 years ago. And think about what Sorry? I mean, Microsoft actually does this right now. If you want, you can download an application and, I mean, you can download a software that can do this for you. How to look up the name of the software, but a quick Google will let you find it. Okay, face detection and tracking. So now, we have seen the applications. Now, let's talk about a temperature sensor. Okay. Temperature sensor, there are basically 3 different types here. A resistance temperature detector, thermistors, and thermocouples. Okay, so do we use any one of this in our day-to-day life, guys? Which one do we use? Or does anybody know what any one of this is? What is it? Which one do you know? Come on.
Yeah, you guys know.
A thermocouple? Okay. It measures the temperature, but how does it work?
That's right.
So let's look here. Thermocouple. Since Scout said thermocouple, we'll start with that. So thermocouple here is nothing but we have on the left side here, if you see, we have 2 metals. There is metal A, metal B. Okay. So if I take aluminum and let's say if I take iron, do they have the same materialistic properties? No, their properties are going to be different, right? So if I subject it to heat, okay, if I take the 2 materials and if I cascade them next to each other, and if I subject it to heat, one is probably going to deform, the other one is going to extend, right? Then if one of them is deforming, the other one is extending, what happens? Are they going to be straight? Are they going to be inclined? Or would they be straight or go concave or convex? Would they be literally straight or varying? If I take 2 different metals and subject it to different temperatures, right? They would be flexing, right? When they flex, what happens is the resistance changes a bit. And what happens here is on the right side we have 2 materials here. When they flex, when the resistance varies, right, what happens to the voltage drop? If I apply a voltage at the beginning, and if I measure the voltage at the end, and if the resistance varies, what happens to the voltage drop? Would it be the same or would it be any different? Ben? It will change, right? And if you know how much it changes, right? For example, if I know, initially if I calibrate the system, if I say the voltage changes by maybe 0.2 volts, the temperature is going to be maybe 70 degrees. If the voltage changes by 0.4 volts, maybe the temperature is 75, right? So you got to calibrate the system. And it works purely based on that. When you have, think about 2 metals, calculate the deformation here, and obtain the voltage difference, and it gives you a relation between temperature and voltage. Okay. Oh, come on. A thermistor. What is a thermistor? Are you guys familiar with thermistors, guys? It's not a transistor.
You guys remember thermistors, don't you?
Okay. Changes based on temperature? Okay. How about WID, guys? The widths.
Yeah. Arnie, what does it do, thermistor, lads? Yeah, so the resistance changes as the temperature changes.
Exactly. It's a simple nonlinear resistor. It's a simple nonlinear resistor with changing resistance based upon temperature. So here, on the left side, I have a simple graph here. Okay. If you see, for the same thermistor, as my temperature is going down, and my resistance is what? Going up, right? Now look on the right side. Let me ask you this, guys. If I look at just only that, what is that called? What is that? Keep this, if you keep the point of thermistor aside, if I have a resistor here, what is that? It's a simple voltage divider, right? So here, the first one here, I have R1, one resistance that is fixed, and the second one is a thermistor, the second resistor, and the resistance could vary anywhere from, let's say, 10 to 10K, for example, right? It's a nonlinear resistor. If I change the temperature here, okay, and what we are saying is, if I cool this down, or if I heat it up, if I heat up the thermistor, what happens to the resistance? If I heat it up, the voltage goes down, right? If the voltage drop across this, the voltage drop across the thermistor goes down, what happens to the voltage here? If the voltage here goes down, this voltage will also go down. Yes? This voltage here, voltage will also go down, right? And if then I can take this and give it directly to my microcontroller, and I can say, hey, I know this relation right here, that my voltage will go down when the temperature is going up, and if I see a voltage going down, can I say my temperature is going up? Yes? Okay. So, is it a good device or a bad device? I mean, resistors, right? Resistors, are they huge? Are they physically big or small? Relatively small, right? So we can implement in a system. Unlike thermocouples, they're huge. We need metals. Resistors are pretty small. You can put them in anywhere. But two things. One is, what is this? And why do we need that? The triangle on the right side, what is that? Amplifier. Why do we need that amplifier, guys? If the voltage drop, for example, if the voltage drop, the voltage changes is because of the change in temperature is only, let's say, 0.3 volts. Okay? And 0.3 volts, you might need a much larger swing. Okay? What do you do in order to increase the gain? What can you use in order to increase the gain? Op amp, right? Or if, for example, or if your voltage, for instance, maybe let's say this is not a positive voltage. Let's say you get a negative voltage, and your microcontroller requires a positive voltage. What do you use? Inverting amplifiers, right? Okay. Or if there is a signal here, there is some noise that you want to filter out. Can we use an op amp for something like that? Yes? No? Yes, to remove some of the noise, we can use an op amp too. Hello? Okay, so let me ask you a different question here. Before I ask, maybe I'll say this. If I take thermistor 1 and a thermistor 2, right? Each of them, this one is going to have a curve that looks like this, and the second one is going to have a curve that looks something like that. Okay? So, two thermistors do not have the same voltage drop to temperature relation at all. So, if you're using a thermistor in a lab, how do we use it? If I want to implement a thermistor in my application, how do we start, guys? You got to calibrate it. And we'll talk about, you got to take your system first, subject it to known temperatures, acquire voltage, and identify the relation between temperature and voltage, store that information, and then deploy it in the test. And you can go the reverse method and say that, hey, for based upon a particular voltage, you can say, here is my particular temperature, right? And in fact, that is what we will do in Lab 4, or in Lab 2 for WID students and Lab 4 for CME students. Okay. Now, bottom line, I want to say is like there are 3 types. In here, shows the difference between each. Thermocouples versus thermistors. Which one is better? For our, as electrical engineers, if you're trying to go portable, and if you're trying to get high accuracy, you want high accuracy, right? Or do you want low accuracy? High accuracy? Low? Depends. Okay. So can you guys think about a time when you would need low accuracy?
So large temperature range.
Yeah, but yeah. Quick response time. So it is, what you're saying is, you are.
If you like look at a control system, right, and it like it goes like immediately goes up, like, or if you want it to go quicker to the like the error, I guess.
Mm-hmm. Yeah, you're talking about trade-offs then. So what you're saying is, I'm willing to sacrifice accuracy for response time, is what you're saying. But is there an application that would say, I want low accuracy?
Random data generator.
Why would you?
You're trying to get with a certain standard deviation and it doesn't matter.
Random data generator, where you want to get data in a certain range and the numbers doesn't matter?
Yeah. You want to generate fake data.
If you want to generate fake data and fake news, no. Yeah, randomization.
If you care more about the change in temperature rather than the precise number, so temperature's going down or temperature's going up.
Yeah. Again, you're trying to randomize things. Kind of. Okay. So, I know the folks there are going to leave in about 20 minutes. So let's talk about this encoders for a second. What are encoders? Encoders are nothing but sensors that measure the rotational motion. Okay. Say, for example, if you have a robot, and if you have a robot with wheels, okay, and if the wheels are moving, and you want to know how far the robot has traveled, or if you want to have a robot go a certain distance, you got a robot which has a wheel. The wheel is connected to a motor, right? And can you tell the motor to go a certain distance and stop? The motor requires only one electrical signal, and the electrical signal is move or stop, right? Turn on or off. But how would you tell it? Or how would you measure how much it moved? So if you have a robot start at a location, it is moving, and I want to measure the distance it moved, how do I do that? We use something called encoders. Okay. Did you guys use encoders before? No? How about the students at WIT? With?
You come across encoders before yet? Not with me, anyway.
No? Okay. So, okay, let's go with this then. It's a fairly simple concept, guys. Okay. What you see on the left here is a simple image of a disk. Okay. It's a rotating disk. And if you see the white points here, these are holes, right? There are holes. So think about a disk, a rotating disk, with evenly spaced number of holes. Okay, and if I have light on one side, okay, or let's say I'm an LED on this side, and a photosensor which senses light on the other side. Okay, so when there is a hole, the LED gives out the light, and the light passes through, right? Yes? When the light passes through, I get a logic 1. Okay? Then the disk rotates, and then what happens is the whole part moves onto the side. Then you have the metal. And if you have the metal, can the light pass through the metal? No, right? And the photosensor, can it sense anything? No light. So then it goes to 0. Then the disk rotates continuously. Then the hole comes back again. You go, the photosensor senses it. You get a 1. Then it moves continuously. You get a 0. You get a 1, 0, 0, 1, and so on and so forth here, right? So now, you get the concept of ones and zeros here. Whenever it senses light, it gives a logic 1. If there is no light, it senses a logic 0, right? Now, if I know the circumference, if I know the size of my rotating disk, if I know the number of holes in the disk, right, can I calculate how far it moved? Right? Take a wheel, put the disk on it, right? And if I know there are 360 holes on it, right? Or let's say 360 holes on it, and if I sense 90 holes, it means I moved 90 degrees, right? If I know the circumference of the wheel, if the circumference of the wheel is 360 centimeters, and if I measure 90 holes, how far did we move? Circumference of the wheel is 360 centimeters, and I have 360 holes, and I have sensed 90 holes. So how much distance did we move? 90 centimeters, right? A simple thing here. Okay, so that is how your encoders work. Let's do a simple math here. Okay, here is a simple robot. On my each wheel on the right side, I have on the right side, my diameter of the wheel is 10 centimeters, and this particular encoder here is inserted here. Okay, and I want to know the 3 questions here. How far does the wheel travel for one encoder count? What happens if the wheel diameter changes? And if I want to travel 1 meter, how many counts should I be getting? Okay, how do we do this? How far does the wheel travel for one encoder count? The diameter is 10 centimeters, right? And what would be the circumference of the wheel? Pi d, yes? So this is going to be 3.14 multiplied by 10 gives you 31.4 centimeters. Yes? Yes? So that is 16 ticks, right? The encoder has 16 ticks. So how much would one tick be equal to? 31.4 divided by 16. Gives you 1 tick, or 1 tick or 1 light sensor value is about 1.9. I can't see, my recorder button is up here, so I can't see the value. 1.96 probably.
Yep.
Okay. So now, suppose I want to move 1 centimeter per count. How do we change it? One centimeter per count. What should our wheel diameter be the same, or should it be different? Different, and that is how you get it. Like Okay? There we go. Okay. Now, let's say if I have the same wheel that is 10 centimeters, how many encoder counts will be there for distance of 1 meter? So we have diameter of 10 centimeters, right? And we want a distance of 1 meter. And what we found is there are 16 counts. 16 counts or ticks in the encoder, right? So what we found is once it does 16 counts, it travels 31.4 centimeters, right? So if I want 1 meter, how many encoder counts will I need? You need about 51 counts per meter. Okay. So if you have a robot and if you need the robot to go in a certain distance, right? So can you do this math and say if I want to move, if you know the diameter of your wheel and if you know the number of ticks on your encoder, can you make the robot go a precise amount of distance? Yes? Okay. Now, a simple question here, a very simple question. Let's say I have a robot with 2 wheels, right? And if I want both the wheels to go straight, okay? Now, how do I control the speed of the wheels? If I want them to go uniformly straight, if they want it to go literally straight. So do I put my velocity and my speed and the distance as the same for both? Or opposite for both, or what? I have a 2-wheeled robot. I want the robot to go literally straight. The 2 wheels are connected to 2 independent motors. Okay. What happens if the motor velocity or the robot velocity is different? Terms, okay? So let me ask you this question here. It is not related to encoders, but thinking along these lines. If I have 2 wheels, the left motor moves faster compared to the right motor. What happens? If the left motor moves faster, it turns to the right, right? If the right motor moves faster compared to the left motor, left, okay? Now, if I have the same, next question is this. I have 2-wheel robot. I want the robot to turn literally 180 degrees with stopping at the precise location. I want it to go 180 degrees. Turn the robot 180 degrees. What do I do? One motor has to stop and the other motor has to turn around. So, see this. If I have this robot, right, what we are saying is if this is stopped and this is moving forward, then this will come back and stop like this, right? I don't want that. I want it to be right there, but instead of pointing this direction, it has to point that direction. Send the same signal to both motors. If you send the same signal, they move forward. Phase in the opposite direction. So we are saying give like a positive voltage on one side and give a negative voltage on the other side, so you can rotate it, right? That is where we call the zero term. Okay. So you can get robot to literally spin in the same direction, and you can get the precise location there. Anyways, so Dr. Walsh, are we doing okay on time, or are we short on time?
You got another about 10 minutes, I'd say, before these guys will be heading for the door.
Okay, we'll make it quick then. So, potentiometers are, what is potentiometer, guys? Adjustable resistance. So, what we know is if this is resistance 10 ohms, right? Now, if I plug in one more 10 ohms, what is my total resistance, guys? This is 20, right? And if I put one other 10 ohm resistor, that becomes 30, right? So potentiometer is nothing but a series of small resistors put together. Yes? I'm trying to explain it to the computer science folks here as well. So the electrical engineers will not agree with me 100%, but can we say that? Is it equivalent? Taking small resistors and hooking them in a series, would we get a long resistance? Yes? It's a simple concept, right? If I have this whole thing as a resistor, right? Okay. And a resistor here, how many terminals does it have? 2 terminals, right? This is terminal A, this is terminal B, yes? And here is my, oh, come on. Here is my terminal A, and this is my terminal B here, okay? So what I'm saying is, this needle here, the needle can rotate here, or the needle can be like that as well. So if I'm measuring the resistance between A and B here, and this is position 1, and this is position 2, okay? If my resistance between A and B is, let's say, 10 ohms, okay, in position 1, what would be the approximate resistance for between A and B in position 2? Higher, lower, same? More than 10 ohms, yes? That is a simple potentiometer here. Okay? Where would we need it? You don't need the resistance you need. Sometimes, yeah, you're talking as a pure circuit designer. If you're trying to design a filter, yeah, probably you got to tweak the resistance to find the precise filter there. Or, let's say, look at this application here. On the right side, unfortunately, you guys cannot see this, but I'm trying to design a pneumatic arm, for example, let's say, and I want to know how much my fingers are bending, right? If I put a thermistor, there is a bend sensor, there's a force sensor, the more I twist it, right, the resistance varies. And if I know the relation between the resistance and my bend, can I know my precise location of the hands? Yes? No? Very much like calibrating your thermistor. Can we calibrate a variable resistance that I put on my hand and calibrate it and know the angle at which my fingers twist and turn? Yes? Same thing here. Okay. So, probably, yeah, let's skip this as well. Accelerometers, guys, we'll talk about this and probably we'll stop for them and we will continue. Accelerometers. Let's talk about this. Is this a important sensor or not so important? In the lift, okay. And do we all carry accelerometers with us right now or are we not? Do we have some kind of accelerometers in our pockets right now? Phones, guys, your cell phone. Sorry. Does your phone have accelerometers? Why do they have accelerometer? What can they do?
Anybody here? What does an accelerometer do on your phone? What is it used for? Yeah, for landscape portrait. You can detect where it's facing down or facing up.
Yeah, the cell phone can tell you if you're facing up or facing down. And Scout, you're saying something about accelerometers?
I was just saying, like, it's got like the heart monitor, it's got all that stuff you want to track it.
The heart monitor? Oh, the cell phone. Yeah. Okay. So, yeah, you have the heart rate sensor in the cell phone right now, and combine that with the accelerometer, you can say, for example, is it as a result of your running, or is it as just as a result of some health issues, right? So yeah, you can use that. But how does it work? How does the accelerometer work? Changes around the axis, but how does it physically work? What's inside? I mean, the accelerometer, it can sense in 3 axes, right? It can sense movement in x direction, it can sense movement in y, and also z. Gravity and pressure? It's actually much simpler than you think. It's a very simple system here. Okay, so what you have here, if you see this on the right side, we have a red electrode number 1, right? That is a small electrode. This red one, number 1, is a small electrode. This purple one is an electrode. The number 6, blue, is a small electrode separated by air capacitance here, right? Now, when you're moving, okay, let's think about this. Let's say your number 1, the red electrode is static, okay? That position is fixed, continuously fixed. It doesn't move. But the other casing on the side, what I'm saying is this particular part is fixed, right? And based upon your movement, this whole casing around it can go up and down if you're moving. Okay? Can you visualize that? This part is fixed and this is moving up and down like this. Okay? So if it is moving, what happens, think about this, guys. This is a metal plate. This is a metal plate. And there is some insulation in between. What did we form? 2 metal plates separated by some insulation in between. A capacitor here, right? Again, a metal plate here, a metal plate here. There is some insulation in between. What do we form? A capacitors, right? So the nice thing is, because of this capacitance, if you're moving, can you measure the variation in both places? Yes? Simple as that. You have x-axis same way, y-axis same way, z-axis the same way. Okay? Measuring capacitances in different directions. Using the capacitance variations, you can easily say how much of acceleration there is. And how rapidly it changes, you combine that with the capacitance value, you can easily say if you have 1g acceleration or a 2g or a 3g or whatever that is. Okay? Okay, Dr. Walsh, I understand we talked about the applications of accelerometers. Let's do quickly light sensors. We said we use light sensors in, for example, your cars. How about the classrooms? Or how about your household applications? Just to save energy, right? We use light sensors there. Or how about sonars? What is a sonar sensor? Are you familiar with sonars? How does they work? Yeah, it sends an acoustic wave, just like a bat. It sends an acoustic wave, and the time it takes for it to go and reflect and hit something and come back, it takes some amount of time, right? The further the distance the signal has to go, it hits something and comes back, the further the higher the time or lower the time? Higher the time, right? The further it has to travel, the longer it takes for the signal to come back. And if you know the relation between the time and the distance, can you tell the robot, if you put a series of these sensors here, okay, on the robot, can you know where the obstacle is? If you place a sensor literally at 90-degree angle, you would know what's in front. But if you place a sensor at a particular angle, if you place a series of sensors along the front of the robot, like the one you see on the right side here, okay, if this is my robot, if I place sensors right up front here, right, and if this sensor on the top right side is telling me there is an obstacle, I would know probably the obstacle at where? 90 degrees? Where? I heard someone was saying something. If you know the placement of the sensor, the angle placement of the sensor, and if a particular sensor tells me there is an obstacle, can we localize that object? Yes? Where do we see these sensors, by the way, now? In everyday applications now? Do we see them in cars right now or no? What are these used for in cars? Parking assistance. Exactly. That is one basic application we see. Photo gates. What is photo gates, guys? Anyone who worked in the manufacturing industry? So photo gates is a simple IR transmitter and IR receiver here. It sends a signal from one to the other end, okay? And if you just want to count how many objects are moving through between here, right? So you can put a simple photo gate, and anytime there is no obstacle here, okay, the signal passes through, right? On the other hand, if there is an obstacle here, no light passes through, right? So can you identify if there is an obstacle or not? And if you put this on a conveyor belt, and if you have a lot of items moving, can you count how many items are moving? Now on the top, now on the top here, put a barcode reader. Okay, you have a photo gate, and you also put a barcode reader on the top. Would it have any application? Inventory, right? And this is kind of like what is being used in the Amazon warehouses to track the position of a box and send it to the appropriate chute and load it on the appropriate truck even. All this photo gate combined with systems in the warehouse will increase the speed of the shipments. Okay. I'll show you a video on that. Then we have gas sensors. Okay. Now quickly, let's talk about connecting this sensors to microcontrollers. Okay. What we have seen is the sensor gives an electrical signal, at times that is analog, at times that is digital. We need to convert that to some kind of a format your microprocessor accepts, right? And connecting here, we have to follow, we have to follow protocol. What is the protocol, guys? A set standard that you have to abide by, a set of rules that you have to abide by. Yes? Okay. And there are different protocols for connecting the different standards we can use, and we will talk about that. There are protocols. Oh, come on. Sorry, guys. There are protocols UART, I2C, SPI. There are different protocols that we could use. Okay. We will learn about these protocols in a week or two. Okay. And quickly, before they go, we'll talk about calibration also next week. Okay. But before we go, let me ask you this question here. I have three pictures here. One is low precision, low accuracy, high precision, low accuracy, high precision, high accuracy, right? So what I'm trying to say here is my plus sign is my actual value, right? So look at the difference here. Both the first and the second one are low accuracy, right? So here, my precision is low and my accuracy is also low. My real value is here. My readings are all over the place. Okay. But look on here on the second graph. The accuracy is very low. So in the sense the reality and the measurement are far off, but they're very precise. In the sense all these values are in one location. Okay. Then the last one is higher accuracy and higher precision. Which one do you want in an ideal scenario? In an ideal scenario, you want high precision, high accuracy, right? But can you obtain that all the time? No. You got to trade off for something. Yeah? So, lastly, I'll ask you this. Sensor fusion. Like, for example, we talked about here in the cell phone, we use accelerometers and a heart rate sensor, right? But or even the Fitbits that we have, can we just use one sensor data and make useful decisions? Or if I combine sensor data from different sensors, will it help us make better decisions? More sensors, like as we talked, if we have a heart rate sensor combined with accelerometer, it can give us a context of why the heart rate is going up, right? Or let's say in the room, if there is a temperature sensor and if there is a PIR sensor, a temperature is going up, you don't know what is the reason. But if a PIR sensor is there, a passive infrared sensor there, okay, it can sense that there are a lot of people in the room. And if it says there are lots of people in the room and the temperature is going up, it gives you a context. Yes? And you can make informed decision based on that. So we have to think about how do we utilize this data efficiently here and form a context around it. Okay, is what we're talking about here. So lastly, what I want to ask is, this one. What are the different factors we have to choose? What are the different factors we got to consider in deciding what sensors to use? What are the factors we typically use as designers? What factors do we use, guys? Accuracy. Cost. How about physical size? Right? Precision. You need precision or no? You need precision. And how about ability to interface? Like if the system sensor says, I'm going to give out only analog signals and you need digital. So, or let's say it can interface only through wire, but you need some kind of wireless transmission. Yes? Or what about operating in different temperature ranges? Think about you're utilizing a small accelerometer next to the engine component under the hood of your car that cannot take much vibrations. Or under the hood of your car near the engine, what is the temperature is going to be? On an internal combustion engine, guys. I'm not talking about electric hybrids, but going to be low or high? Ben, you said pretty high, right? And if your accelerometer cannot take the temperature, will it work? It might work for the time being, but within no time, it's going to stop working, right? So there are different factors that we got to consider when choosing a sensor, okay? So probably with that, we'll stop. And when we come back, we will talk about analog to digital converters, digital to analog converters, and after which we'll talk about interfacing sensors to the microcontrollers.
Okay.
So I'm stopping.